Hi, I'm Patty Fraser-Locke, and this is a brief introduction to Bootstrap confidence intervals. Bootstrap confidence intervals are a way to create confidence intervals using only the data in your sample and some very basic ideas from descriptive statistics. So bootstrapping, key phrase, let your data be your guide. This method was developed by Brad Efron at Stanford University. It comes from the phrase pulling oneself up by one's bootstraps, which refers to reaching down, grabbing the straps on your boots and lifting yourself right off the ground, which seems impossible. It is impossible, and this method seems quite amazing also, I think, the first time you see it. So bootstrapping works because we assume the population is many copies of the original sample. So let's look at an example. Suppose we have a random sample of 6 people. Here are our 6 people, and we're measuring some statistic with these people. Measure maybe the average IQ or the proportion who voted in the last election, or correlation between height and weight, or some sample statistic we're computing from this sample of 6 people. For bootstrapping, we take our original sample and we assume that the population is many copies. So this gives us a simulated population to sample from. So here is our original sample of 6 people. Notice that the simulated population is just these same 6 people repeated over and over again, infinitely often. So what does this mean in practice? We sample with replacement from the original sample, since each of these people represents many others in the possible population, using the same sample size, because we're estimating variability here, and sample size is key. So we're taking a sample of size 6 with replacement from this original sample. So let's do that. We sample one person and we get this blonde person, and we sample again, we get the red-headed person. We sample again, we get the blonde person again. Remember, that's possible because we're sampling with replacement and because this person represents many people in the population who have the same characteristic. We sample again, we get this person, or this round person, get the round person again, and finally get this rather scary looking person. So this is one bootstrap sample starting with our original sample. So again, we assume the population is many copies of the original sample. The key idea to see how a statistic behaves, in particular to measure the variability in the statistic, we take many samples with replacement from the original sample using the same sample size. So let's look at an example. What is the average price of a used Mustang car? So one of our students did this, selected a random sample of 25 used Mustang cars from autotrader.com, and recorded the price in thousands for each car. So here's a pictorial representation of our sample of 25 used Mustang cars, and there's a dot plot of the cars, and there's the sample size, mean, and standard deviation. Again, this is all your students need to know in order to be able to start constructing and understanding confidence intervals. So our best estimate for the average price of used Mustangs is $15,980 from this sample mean, which is in thousands of dollars. And the question is, how accurate is that estimate? We want some kind of confidence interval or margin of error to put with that best estimate. Key question: how much can we expect the sample means to vary just by random chance? So here's our original sample again. We take a bootstrap sample, which means sampling with replacement with a sample size of 25 from that original sample. And so here's our bootstrap sample. Notice that this blue Mustang car got selected 3 times over here. This gold Mustang convertible did not get selected at all in our bootstrap sample. Same idea, same pictorial as we had before with the 6 stick figures. So here's the idea. We have our original sample, and from that we compute some sample statistic that we're interested in. From the original sample, we construct many bootstrap samples, doing this over and over again. We compute the bootstrap statistic, same statistic as the sample statistic, over and over again, and we gather all of those into what we call the bootstrap distribution. And because we want to do this thousands of times, we need technology. And so we have developed a set of tools that enable this to be done quite easily. They're freely available to everyone at lock5stat.com. There's another one of these introductory videos that explicitly talks about using StatKey if you want to take a look at that. So let's go to StatKey now, and here is the main menu. Here are Bootstrap confidence intervals here, and you get there by going to lock5stat.com. And we're interested at the moment in a confidence interval for a single mean. Notice, however, StatKey has descriptive statistics, confidence intervals, hypothesis tests, sampling distributions, theoretical distributions, and more advanced randomization tests. At the moment, we're doing a Bootstrap confidence interval for a mean. Let's go there. There are many built-in data sets connected with our book, Statistics Unlocking the Power of Data. One of them is this Mustang price data set. So let's go there. And you see right here, this area will always have the original sample. And notice that here's the dot plot we saw earlier, although now we can hover over the points and see that this very expensive Mustang car was $45,000. Here's one for $37,900. Some very cheap ones also down here. Here's the sample size, the mean, median, standard deviation, all that we saw earlier. Okay, we're going to generate one Bootstrap sample. Here it is down here. Notice that this expensive $45,000 car did not get picked. Two of these three got picked. These three of them got picked twice. So this is a Bootstrap sample, just as we talked about it earlier, sampling with replacement from this data set with sample size 25. We've computed the mean. It's 14.328, and that 14.328 is plotted over here on this area, which will become the Bootstrap distribution. So again, this is the original sample. This is the most recent Bootstrap sample, the only one so far now. And this is the Bootstrap distribution. We generate another sample, and again, we didn't get the expensive one. We got both of these, but not the two more expensive than that. These ones we got picked many, many times, all at 7 here. So there's 2 7s here and a whole lot here. Again, another Bootstrap sample. This mean is 14.484, and now both means are plotted here. We can generate another sample. We get this one, 16.38. We see that plotted here. We can generate another one. 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 You can hover over any of these and see the Bootstrap sample that gave rise to that Bootstrap statistic, that Bootstrap mean. Okay, let's generate 1,000. So there is a Bootstrap distribution. We can generate another 1,000 if we want. It doesn't take very long. And again, still hovering over these will show you the Bootstrap statistics. So if you watch over here and try not to get seasick, you can see that every one of these gives us one. We can see why these are quite a bit out in the upper tail, and we can see that that's because those Bootstrap samples happen to over-sample these expensive cars. Down here at the other end, these small ones are so small because they didn't end up getting these. So you get to talk a lot about randomness and variability in the sample means. These values here, it tells me that I happen to have done 2008 Bootstrap samples at this point. Here's the mean of that distribution, and here's the standard deviation of that distribution. And that standard deviation is really 2.134 in this case. It's just the standard deviation of all these 2,000 plus Bootstrap statistics. If we go back to the slideshow, here's a previous simulation that we did, and that value, that standard deviation of these Bootstrap statistics, is an estimate of the same of the standard error, the same standard error that we can find by formulas also. And so how are we going to So there's two ways to find a Bootstrap distribution, to use a Bootstrap distribution to get a confidence interval. The first way is to use that standard error. So the standard deviation of the Bootstrap statistics estimates the standard error of the sample statistic, and a quick interval estimate is to use the original statistic plus or minus 2 times the standard error. So for the mean Mustang price, this original sample mean was 15.98 in thousands of dollars, plus or minus 2 times the standard error that we found from the Bootstrap distribution. And we compute that to be 11.624 up to 20.336. There's a second method to use the Bootstrap distribution to get a confidence interval. And so let's go back over to StatKey to find that. And actually, let me click one more time here. Instead of using the standard error to estimate the middle 95% from the empirical rule, we can find the middle 95% directly, since we have all of those sample means, Bootstrap sample means stored. So now we'll go back over to StatKey. There's a two-tail button here, and if you click on this, 95% is the default, and it keeps 95% in the center here and cuts off 2.5% from each tail, giving a 95% confidence interval of $11,856,000 to $20,153,000. Very similar to what we found using the other method. We find that both these methods are really valuable. This method is a wonderful visual display that helps students really think about 95% intervals, and the other method kind of sets them up for later on in the course. In Chapter 6, we go back and do the shortcut, what we call the shortcut formulas, and they're all set up to take the sample statistic and add plus or minus something that has to do with the standard error. And so they both really lead them to a deeper understanding of a confidence interval and to what is to come later. Again, the only thing they need in order to get to this point to really understand confidence intervals is being able to read a dot plot and knowing about sample statistics, means, proportions, difference in means, those things. Okay, let's go back to PowerPoint and look one more time at this Mustang prices. And so again, we keep the 95% in the middle, chop 2.5% off of each tail, and always interpret in context. For this simulation, we're 95% sure that the mean price for Mustangs is between $11,930 right there and $20,238 right there. So we keep the 95% of statistics and look at these values to give us the 95% confidence interval. And one more thing before we leave. There's the standard deviation from the simulation, 2.178. You'll get slightly different answers with different simulations. That again is the standard error. And here we show the shortcut formula. This is a sample mean, so the standard error is s over the square root of n, and it's very, very close to what we get with the simulated Bootstrap standard error. Okay, let's do a second example. This one is for a proportion. And so this is a poll of likely voters in October 2012, just before the presidential election of 2012. The poll asked 722 likely voters in Ohio who they planned to vote for, and 368 choose Obama, 339 choose Romney, 15 choose otherwise. And we want to find a 95% confidence interval for the proportion of Obama supporters in Ohio. So remember those numbers. In our sample, 368 choose Obama out of 722. If we go back to StatKey, now we want to go back to the main menu. Now we're doing a confidence interval for a proportion. And there's an edit data key. You can edit data. You can enter your own data in any of the options. It's easiest to enter for a proportion because we just need to know that it was 368 out of 722 likely voters. And there's our original sample again. We can generate a Bootstrap statistic. It works exactly the same way, same sample size. Now we are sampling with replacement from voters who are picking either Obama or not Obama. And for this particular Bootstrap sample, we got 355 out of 722.492, and it's plotted here. We can generate some more. We can generate 1,000, and we can find either use this standard error there or use the 95%, and we get 0.472 to 0.546. as the proportion, as a 95% confidence interval for the proportion who plans to vote for Obama in October of 2012. Okay. Using stat keys, so here's another simulation, 0.018, almost exactly the same as we had on the previous simulation, and 95% here. We could also use this standard error using the other method. The original statistic is 0.51, plus or minus 2 times the standard error, and we get 0.474 to 0.546, almost exactly the same as we get using the exact 95% of samples in the middle method. Okay, let's do a third example, Diet Cola and calcium. So the question here is, what is the difference in mean amount of calcium excreted between people who drink Diet Cola and people who drink water? So in this experiment, they had 8 people in each group. One of the groups of 8 drank Diet Cola, the other group drank water, and then they collected their urine for 3 days afterwards and measured the amount of calcium in the urine. And the instructions are to find a 90% confidence interval for the difference in means. So we go back over to StatKey and back to the main menu. Now we want to do a confidence interval for a difference in means. And so we get to here. The calcium in Diet Cola is one of the included data sets. So here is the dot plot. Here are the amount of calcium excreted for the water drinkers. Here's the amount of calcium excreted for the Diet Cola drinkers. There's some overlap, although it looks like the Diet Cola drinkers leach more calcium, and that's the question, whether Diet Cola does leach calcium out of the system. So we generate one sample, same method always, which makes it really quite easy for the students to digest. Here we're taking a sample of size 8 with replacement from the water drinkers to get this Bootstrap group, sampling with replacement from the Diet Cola drinkers with a sample of size 8 to get this Bootstrap group. The means here are 56.875 and 49.25. The difference in means, which is the statistic we care about for this Bootstrap sample, is 7.63. And we can generate another, generate another, generate another. Again, we're building up our Bootstrap distribution on the left there. Generate 1,000. And if we do a two-tail, the default is always a 95% confidence interval. But to find a 90% confidence interval, we click on this box here, put in the fact that we want 90% instead of 95%, and there's our answer. We are 90% confident that the difference in amount of calcium excreted between Diet Cola drinkers and water drinkers is 3.375 to 10. Okay. So, why does the Bootstrap work? So here is a sampling distribution. We have some population. There is some mean for this population. It's fixed. We don't know what it is. We sample from the population, and there's one of our sample statistics. Notice that it's not the same as mu, but it's not that far off. Take another sample. It's not the same as the first sample, so the students get this idea of sampling variability, and it's not the same as mu, but they're close. Take another one and take a whole lot of them, and we're creating a sampling distribution here so that students see the familiar shape of the normal curve. They're clustered around, centered at mu, and they have a certain variability depending on variability of the original population and sample size. So this is great. We want students to have this image in their head, but in practice, we don't see the tree. We don't know the entire population. We don't see all the seeds. We only have one seed. So there's our one seed. If we're estimating a mean here, that's our sample mean. What can we do with just one seed? And maybe you all repeat in tune with me. We grow a new tree. And that's what bootstrapping is all about. We create the simulated bootstrap population from the sample that we have, and we sample from that simulated bootstrap population. And the amazing thing is we get a sampling distribution that's very similar to the sampling distribution from the entire population. And so there's our sampling distribution. And we estimate the distribution and variability, or the standard error, of the sample means from these Bootstrap statistics. There's our mu from the original. And so the golden rule of Bootstraps here is that the Bootstrap statistics are to the original statistic as the original statistic is to the population parameter. That makes the whole thing go. Thanks for listening, and if you want additional information on Bootstrap statistics, you can find it at www.lock5stat.com. Thanks very much.